Hello everyone, and welcome to another complimentary Green Tech Media webinar. This webinar is part of a series of webinars we do throughout the year to help keep professionals in the grid edge ecosystem informed through research and analysis on the latest technologies and market trends. Today's presentation, Distributed Energy Resources, Seizing Opportunities While Managing Distribution Grid Impacts, is brought to you with support of our sponsor, ABB. I'm Ben Kellison, the Director of Grid Research for GTM Research, a Wood Mackenzie business, and I'll be moderating today's webinar. Green Tech Media is an online publisher for information on the grid edge ecosystem as well as renewable energy technologies. GTM Research is the market analysis and consulting wing of Green Tech Media. You can stay informed by reading our news at greentechmedia.com and find out more about our research products by visiting gtmresearch.com. You can also click on the GTM icon at the bottom of your screen for more information about our company. Before we get started, I'd like to run through a little bit about the screen you see in front of you to make the most of our time together today. You'll notice that there's a dock along the bottom of the screen with several widgets. Some of these widgets that may be of interest include the Download Slides widget, which is a link to the PDF of today's presentation. On the right side of the menu bar, there's a Speaker Bios widget, where you can get a little bit more information about the speakers that are joining us today. There's also a widget to share this webinar through your preferred social media outlets, as well as a place to download some resources similar resources from our sponsor. Please note that at any time you can enter questions throughout the presentation through the Q&A box that's located on the left-hand side of the screen. If you have any technical questions, this would also be the place to enter them. We'll be answering questions related to content in the last 10 to 15 minutes of the webinar and answering technical questions throughout the webinar. Lastly, to enlarge the slide area, feel free to click on the expand arrow button in the center of the presentation, on the top of the presentation window. Before we go any further, I'd like to introduce our speakers. We have Chip Fox, the Director of Energy Portfolio Management with ABB Enterprise Software, as well as Tom Bialik, the Chief Engineer with San Diego Gas and Electric. Today's presentation will be broken into 4 parts. We'll first examine a little bit about the distribution energy resource deployments and growth trends. Following that, we'll look at a little bit at integrated solutions for DR management, and transition into a little bit of view of managing the future utility with Tom's presentation on some of SDG&E's experience integrating distributed energy resources. Lastly, as mentioned before, we'll go through a Q&A section for about 10 to 15 minutes at the end of the presentation. So with that, I'd like to talk a little bit about how DR penetration has changed over the last 5 years with the United States and what we're seeing looking forward. Distributed resources have been around since the beginning of electricity, but it's only been in the last 10 years where we've seen a kind of shift towards integrating those resources in a much more important way within the energy system as a whole, as well as energy markets, and to meet customer needs locally. It's something we've not seen since the early days of electricity generation. So when we look at that, I just wanted to kind of go through some of the buckets that we see as some of the more important buckets within the distributed resource marketplace that are really seeing the growth or represent a significant portion of the existing capacity. So when we look at demand response in the United States, for instance, when we look at specifically demand response in ISOs, we see almost 30 gigawatts of resources. Now, this is down a little bit this year, but that resource level is not, and it's fairly consistent overall. But that resource level is only within those ISOs, and we see a little bit more interest in that from a utility perspective. A lot of that drop is something where we're seeing kind of a shift away from traditional backup generation. And when we look at distributed energy resources traditionally, market interaction has largely been driven through these demand response programs at the ISO level, where we've seen a significant amount of those resources actually be behind the meter generation. And as we move forward within the wholesale markets, we're seeing increasing interest from many other types of distributed resources that have just traditionally not interacted with markets, such as distributed solar or energy storage, and integrating into some of these traditional programs as they change to adapt to a more distributed electrical system. One thing we have seen that's particularly interesting is most of the drop this delivery year in the amount of available resources is due to reciprocal internal combustion engine EPA regulations that have removed much of the potential for diesel backup generation to be a big part of that behind-the-meter generation, that 5 gigawatts and what was over 6 gigawatts of behind-the-meter generation in PJM and MISO specifically. And we've seen actually a drop of over 1.5 gigawatts of resources in that area. Moving on from there, if we look a little bit deeper in kind of a little bit of the future, PJM runs the only 3-year ahead capacity market out of those ISOs. And what we see is a tremendous shift when it's a conversation within PJM around capacity performance and actually making these resources a more integral part of day-to-day operations and market operation. We do see, because of that shift, because of the customer education associated with transitioning demand response players to a more accountable and more consistent interaction with the market, we do see that shift as something that is has lowered the amount of capacity that has been procured in the out years, out in the 2019-2020 year, as well as the 2018 to 2019 delivery years. But what's interesting is you don't see as strong of a drop in the percentage of capacity acquired by PJM for those resources. So it actually hasn't really changed as a percentage of the energy ecosystem at the wholesale level, but there has been that a stronger change in the actual procured amount as demand response providers work with their customers to integrate them into these new programs. Shifting gears a little bit, we look at more traditional markets. CHP, as well as now fuel cells, which in many cases can be utilized as a CHP unit, have been around since essentially the beginning of the electrical system, and saw massive growth in the 1950s to 1990s, 2000 period, but have largely been a pretty stagnant resource in installs over the past 10 to 15 years in the United States. And we are seeing, that trend continue over the next 4 to 5 years. However, 2020 we expect some growth, largely due to incentives and efforts to make it easier to deploy CHP we see around the country today. These projects do have much longer lead times than many of the other resources that we're discussing today. But because of that, we're expecting some growth. And what's very interesting about these is CHP is not necessarily always distributed. In many cases, in the vast majority of the resources are over 50 megawatt facilities. But what's interesting is we're seeing the growth really coming from the non-industrial facilities. So under 50 megawatts, in many cases under 10 megawatts. Facilities that are actually serving single site customers that don't have nearly the power requirements that are needed for many of the other areas. Moving on, just wanted to give a little bit of a view of the CHP market as a whole. When you look at that market, it is very concentrated. Much of those resources are located in a few states, and it's largely tied to that industrial piece. But as you look forward, areas such as the Northeast, we're expecting some pretty strong growth, strong for the CHP market, that is. And really, that's where we're seeing much of the activity happening lately. Looking at distributed solar, obviously, for many in the audience, this is by no means a surprise. The distributed solar market has grown a tremendous amount over the past 6 years, 7 years even. In the overall solar market, much of the kind of high tail, much of the driving force between growth year to year has been utility scale. But if you look at the two bottom colors on this bar chart, what you'll notice is that the growth of distributed solar, especially residential solar, has been kind of a bedrock piece of the kind of continuing trend towards growth. And over the next 5 years, we see that only continuing. When you look at this next chart, the utility market as a whole, when you look at a year-to-year growth of solar, is something that's driven as a much more volatility, largely due to the ITC, than the commercial solar and residential solar markets. So what we're seeing is a continued growth in those residential and commercial markets, while the utility scale solar efforts have largely been driven to a very strong effort to get deployments in 2016 that kind of abated as the ITC extension came through earlier in the year, and as we saw many of those projects move over and roll over to the 2017 period, and kind of a little bit of a gathering period in 2018 as the market returns to a bit more of a normal cadence as the policy risk has dropped within the U.S. Wanted to go in a little bit of storage. I'm not going to get too deep into this, but because it has kind of an emerging area that hasn't had a ton of activity really until the last couple of years. But we are expecting some essentially exponential growth within the storage market, and by 2021, upwards of over 2 gigawatts total in deployments. This has largely been driven, initially at least, by reductions in cost of storage prices, as well as new potential ancillary services within PJM and opportunities in other ISOs for those ancillary services, as well as obviously a major procurement, major targets in California initially, and now within Massachusetts and several other states. So what's particularly interesting within that, not many of these projects will obviously not get put into place, but even in the last year, we've seen a growth in the amount of in the storage pipeline that's at least in the planning process by over 4 gigawatts, and that's a 66% increase in the amount of storage that's actually within the pipeline. Lastly, I just wanted to touch on one of the ways that many of these resources are coming together. It's not necessarily the primary way, but when we look at the microgrids market, we've actually had to adjust our market forecasts up quite a bit because we have seen some pretty strong several rather large projects go in and get into place over the last 9 months. But we're seeing upwards of likely 4.3 gigawatts of microgrid installed capacity within the U.S. by 2020, which is a pretty strong difference when you look at the market even 3 or 4 years ago, really just pushing past the 1 gigawatt marker. And this is where many of these resources obviously come together to create an energy system that can really help out a selection of customers or a single customer. So with that, I'd like to turn it over to Chip that can talk a little bit more about the technologies integrating these resources.
Okay, thank you, Ben. As Ben mentioned, I'm the Director of Product Management for Energy Portfolio Management Solutions within ABB Enterprise Software. And before I get started, I'd like to just give a quick introduction on ABB Enterprise Software, which along with ABB Microgrids and Distributed Generation and Grid Communication comprise the Grid Automation business unit of ABB. Collectively, we provide solutions for optimization and management of power generation, transmission, and distribution. Enterprise Software provides solutions for asset and workforce management, real-time controls for network and market operations, portfolio optimization, forecasting, market data, and consulting services. We're approximately 2,000 industry and process experts in 37 countries working to improve our customers' uptime and profits while reducing risk, ensuring safety, observing regulatory compliance, all to achieve a stronger, smarter, and greener grid. If you've seen our white paper that we sponsored with Green Tech Media, Distributed Energy Resources, Seizing Opportunities While Managing Distribution Grid Impacts, we address a number of value propositions for DER. This list is certainly not exhaustive, but some of the ones that we include here are load balancing and peak shaving, which is the dispatch of DER to satisfy demand either locally or regionally or to shift peak demands. We see customers or prosumers installing DER for purposes of energy independence or to achieve personal or corporate green objectives or to improve reliability or to reduce energy expenses. We see third parties installing DER to aggregate to a commercial scale to sell energy or even ancillary services into wholesale markets. And we see transmission distribution system operators installing DER to extend the life of grid assets or to defer capital expense for grid expansion. So these are some of the common business cases driving DER investment. As I said, there are others, but What I want to talk about this afternoon are the integrated systems and business functions necessary to achieve these economic objectives. So, in the middle of this slide, we see a number of functions that require either new systems for management of DER or perhaps existing solutions which need to accommodate new capabilities for high penetration DER. 10 minutes isn't really enough time to drill into depth on any one of these items, but we can do a high-level review here. So starting with distribution planning. So this covers both long-term build-out of infrastructure to support DER as well as short-term planning to accommodate installation at specific customer sites. So there are popular desktop applications for performing this process. This process requires assessing the capacity of the local grid to absorb the DER and assessing the current condition on the affected substation and feeders, assessing the potential for reverse power flow, risk to neighboring customers of either increased voltage or frequency variation, and increased cost of wear and tear on utility assets. This may result in the need for additional or updated breakers, switchgear, or increased transformer capacity. And if so, this must be negotiated with the DER developer and may result in new assets being delivered into the field. So once the equipment and inverter are installed, the DER must be registered with the local distribution system operator. And so this can be initiated either by the DER owner, the operator, or the field technician. This can be through a secure customer portal that might be part of a DERM system, or it can sit upstream to your DERMS as an extension to an existing customer portal or to your CRM system, with the information being fed into your DERMS via an API. So either way, this needs to be a flexible model so that it can easily support the addition of new attributes or new relationships as the market or the regulatory environment evolves. So it should also include some ability to monitor the status of the resource and also enable workflows to govern any testing requirements prior to enrollment or prior to the delivery of power services onto the network. Continuing on, we see that the DER should obviously be connected and incorporated into your distribution network model. So this connection can be made either by a common resource ID, maybe the meter ID during the registration, or imported from your GIS. The connection to the network model should enable a geospatial view of the distribution network with regional aggregations, either at a substation or feeder level, and also the ability to zoom into individual DER. So a key feature of any DER management system is the ability to predict what your customers are going to deliver at any time. So demand forecasting, it used to be an easier task when all load was positive and it could all be aggregated and then correlated to the closest airport. However, with the increase in DER and the ability for reverse power flow, the impact of localized weather impacts net demand, and this has become a greater and more important challenge. There's a need for forecasting both demand and generation, and what we can also refer to as either phantom load or shadow demand, or the demand is being served by local generation, but may suddenly reappear on your network if the weather were to change and a cloud blow in. Fortunately, there have been improvements in neural network and machine learning technologies for forecasting, and there's been a huge increase in the amount of local weather sensors with greater granularity, providing fine-grained measurements and prediction for cloud cover or solar irradiance. The key to DER management, obviously, is the ability to monitor and control DER through two-way communication with the inverter. And previously, this has been somewhat limited to either to proprietary protocols or to limited capabilities under IEEE 1547. However, with IEEE 2030.5, this will greatly expand with more capabilities for plant and device registration, for subscription management, and for program and aggregator management. And we'll see this in use in California soon. The DERMS should be integrated into your advanced distribution management system. And in fact, a lot of ADMS vendors are viewing DERMS as a natural integrated extension of their ADMS. This provides fine-grained forecasts for DER generation and demand, and provides important input to the ADMS applications such as state estimation, Flitzer, and VVO, VVC. So in order to effectively manage DER, you need to be able to manage them in aggregate, and systems should support aggregation, not just along the physical network resource, but also by other parameters such as geography, resource type, third-party provider or aggregator, or by the types of services in which the customer resource can provide to the network. Optimization can take on a number of different flavors. This can be optimization of resources to facilitate the VVO programs, or it can be the dispatch of resources to operate within the limits of a given network or resource constraint. The optimization should be able to schedule the best mix of resources according to the various objective criteria. And this can be least cost, maximizing profit, or to meet the environmental criteria. Optimization engines can range from simple heuristics to more advanced solutions such as mixed integer linear program. And this requires some capability for disaggregation of aggregated offers. These aggregated offers can span multiple network resources, and the ability to identify and dispatch resources based on location and the type and quantity of the service offered. The solution must combine multiple resource types, including generation, storage, and even demand response. So as distribution markets evolve, we'll see more requirements for participation in these markets, and these can be applications for submittal of bids and awards, for transaction management between prosumers and consumers, and settlements between parties for the procurement and delivery of these services. So along the left-hand side of this diagram, you'll see some different inputs and the source systems necessary to perform these functions. We talked about integration with GIS and with customer management systems. Obviously, we'll need weather data to feed the forecast. We'll also need meter information to develop the forecast models, market information, maybe locational market marginal prices to drive economic decision making, and we'll need to communicate with third-party aggregators. Along the right-hand side, these functions are either enabled or are enabled by real-time communication with resources in the field. And these resources can range from connected microgrids and the ability to sync between SCADA and the local microgrid controller as they alternate between connected and islanded operations. This can be utility scale DER, which can be controlled either via D&D or Modbus. We've got aggregated DER, which is dispatched from aggregators, but based on either top-level or aggregate requests from the market or network operator. You could see the utility AMI infrastructure may offer a communication network with DER, or prosumer DER can be accessed via the internet and prosumer's home Wi-Fi, either for communication with smart inverters or home or building management systems. So as I mentioned when I initially started talking to this diagram, there are a number of system components and business functions which must cooperate in an integrated manner to reliably and efficiently operate DER. And automation and integration are key to this. So this is illustrated on my next slide. And don't worry, I'm not going to spend 30 minutes reviewing each one of these boxes and arrows on this diagram. I just wanted to put this up to illustrate the potential number of processes, requests, legacy systems, and data exchanges which can exist in the complete life cycle of a distributed energy resource. This is a process diagram that we developed recently with working with a customer on the asset and work management processes related to the delivery, installation, and maintenance of DER. And as I said, this is just an illustration of the importance of integration and automation. So this concludes my presentation. I just wanted to summarize in closing that there are several use cases which deliver value from distributed energy resources. Again, those included load balancing, peak shaving, capacity firming, market participation, and deferring grid investment. And of course, these are going to vary by local regulation and markets. But if you add into this mix the growing interest in increasing grid resiliency through community microgrids, and distribution networks are going to get more complex to manage. This trend will continue to grow as distribution market opportunities evolve and bring more players into the market. It's the vision of ABB Grid Automation and Enterprise Software to enable distribution network operators to efficiently manage the entire life cycle of high penetration DER from customer registration through control while achieving the safe, reliable, and efficient delivery of electric power to consumers. So I want to thank you for your time and interest. And at this point, I'd like to turn the presentation over to Tom Bialek.
Hi, it's Tom Bialek. Good to be with you this afternoon. What I'm going to try to do here in about 15 minutes is sort of walk you through some of the things that we at SDG&E see as far as, how do we look towards the future and how do we manage that future and what types of things are perhaps different, what is changing, what does that really mean for the future grid, and some of the challenges. You heard Chip talk a little bit about the systems that are being put in place. Well, we clearly have a lot of those systems in place as well. It's too bad Chip didn't have time to walk through his big convoluted slide with all the arrows. It's really quite interesting to see all the different things that touch an endpoint. And I think that that's one point that I think a lot of people really don't necessarily appreciate, is that as a utility we have a lot of different systems and a lot of different interfaces to systems. And that's part of the challenge here. Ben talked about what are we trying to do, what does the world look like from their perspective. You saw sort of the forecasts, and it's pretty clear that we see a lot of DER actually coming onto our system. We're currently at, significant numbers. Talk a little bit about that. Talk a little bit about storage, and then some of the work around microgrids and sort of the role that we see that playing. So with that, go to the next slide. So I think one of the things that, that sounds really easy, but this is really the goal. This is the goal of either the grid operator or the distribution operator. It's really to reliably match generation of load while maintaining voltage, power factor, frequency within appropriate limits. Managing the contingencies associated with that, and avoiding overloading equipment while managing power quality. Sounds really simple, and if you think about it in the context of the California ISO grid, where they may have 2,000 generators participating in markets, if you look at what that means as we move to this high penetration DER future, and some of the future models that exist, it's going to be really quite interesting and really quite challenging, and the complexity associated with doing that it's actually very large and increasing. And that's sort of what that particular slide that you presented actually really sort of tends to show, do a good job of showing. So what we'd like to liken this to is that the grid's evolving. Similar fashion perhaps to mobile. But at a different pace, and I think that's and different sort of rules, if you will. You have the traditional basic generation to the actual central station generation through transmission to substations to distribution and out radially. But clearly within the context of this new grid with regards to sustainability goals, you're seeing the addition of more large-scale utility solar, wind, as well as residential rooftop solar. We then get into the elements with regards to sort of the modernization of the grid, implementing more automation, more sensors, more technology, and layering effectively a IT and communications layer on top of the grid. And then lastly, ended up with arguably a self-healing grid where things occur in an automated fashion. So really very different world than where we were. In particular, it used to be that the only way we knew that there was an outage was when customers phoned. And it was really pretty interesting because we still get phone calls 2 o'clock, 3 o'clock in the morning. You think no one would be up, but indeed they were. And now we're getting that same information from our AMI system. We've talked to a lot of people around AMI. They think that, well, you're going to get notification, much earlier and therefore have worse performance characteristics from a safety perspective, but actually the opposite is true. You know earlier, you dispatch the crew sooner, and you actually know when they turn off. And so there's a lot of interesting sort of operational and efficiencies that have occurred via our AMI deployments. So what's happening in California? You're seeing here, this is just a tip of the iceberg as far as what California has done with regards to reduce emissions and empower customers. You see GHG goals, you see RPS goals, and you can see basically SB 350 moving the RPS there to 50% by 2030. We're currently at a nominally 33% level today, moving potentially to 40% by 2017, 2018. So it'll be interesting to see what happens in time. Various initiatives, energy metering 2.0, basically which SDG&E has now rolled into. We've got feed-in tariffs, low carbon fuel standards, market deployment, energy storage, various things, distribution resource plans, Rule 21 interconnection, clean smart inverters, and then just the whole concept of zero energy homes, both from a residential commercial perspective. And I think the point here is that there are changes that are going to be required in the industry to achieve this transition and make it achievable in the long term in a cost-effective manner. So what does that sort of future look like? This is an example of SDG&E. And what I show you here is effectively our duct curve. Certainly much smaller ramps than what the ISO is seeing. But what you see embedded in the middle is basically solar and some of the intermittency associated with solar. Now, a lot of people will tell you that the challenges associated with rooftop solar are really limited to the distribution system, but when you think about aggregation of those numbers into the transmission system, it becomes also a transmission issue. So, for example, we have roughly 100,000 rooftop PV systems today, contributing roughly 680 megawatts. And if you look at that, say, first off, it doesn't count towards the RPS goals in California. That's just where the rules are. But this data shows power production at a 1-second interval, shows highly intermittent power production. And we're seeing that because of the marine layer impacts in California, a lot of, in many cases, no diversity with regards to some of the rooftop solar. So this, you can imagine a 680 megawatt power plant sort of bouncing up and down, and the challenges that creates, not only with regards to a ramp, but also trying to smooth out and mitigate any sort of transmission or distribution issues. And that's really some of the reasons around, we'll talk a little briefly about the sort of smart inverters and why we've gone down the smart inverter road. So what do we see that we need moving forward in the future? We certainly see from a system operation perspective, and it's sort of been alluded to already, forecasts. Forecasts of weather, forecasts of load, forecasts of generation. We're looking at timescales of day ahead, hour ahead, in real time. Typically, 20 years ago, these were, really not considered at the transmission level and certainly not considered at the distribution level. But it's pretty clear from our perspective that even at the distribution level, we are going to need this type of information to actually run the system in a streamlined fashion. Then you can look at the network models, three-phase unbalanced load flow based upon GIS information, looking at not only the load data, but the generation data, state estimation, and contingency planning. So that's part of the challenge around these models. So I'm here at a conference in DC today talking about an integrated grid and some of the needs, and people are really quite surprised that, what level of information do we have, what kind of systems do we have, and what visibility do we have. And keep reminding people that it wasn't until really about 2 years ago, if you talk to any distribution planner, what you would find is that they were concerned with really the peak load and the low load period. And they modeled that, and that's all they modeled. Now we're moving into quasi time series or dynamic time series analysis on 8760 load profile basis, and we're pushing the vendors with regards to software to actually keep up and provide information. And then as we think forward, looking at optimization algorithms, not really, just dispatching load and generation, but how do we actually optimize that while maintaining these voltage, frequency, and power factor with appropriate limits, and how can we do that economically? So, from a distribution perspective, we see that, this is a typical diagram, two-way power flow, distributed energy resources, whether it be in the home, whether it be commercial buildings, or be standalone systems, storage, whether it be substation or distributed, or even in customers' homes. And then how do we leverage systems that we've put in place? Our existing AMI system, which originally was built for billing, but now we're looking at it to say, you know what, we want to do more than billing, okay? We want to get the voltage data out of the meters. And part of our challenge then is how do we do that? Because the system was built as a billing system, and therefore, what changes do we need to do? How do we work across the silos in the utility to get that data information and, get people who are concerned about billing to be concerned about operational issues? Implementing new tools and systems. Lots of people have heard about ADMSs. We have deployed one in ours, Advanced Distribution Management System, which gives us visibility, gives us three-phase unbalanced load flow models, gives us preferred switching plans, and gives us flitter or basically automated switching capabilities, things that historically we did not use because of the systems were unavailable and the operators' unfamiliarity with these automated systems. But we've since implemented these and seen commensurate changes in some of our reduction in outages at times. Modeling, really looking at a whole suite of advanced tools. And not only to monitor and control the distribution system, but you think of this in the context of how does the sort of the integrated T&D system look? Because as the aggregation of units roll up, if you start to get reverse power flow out of the distribution substations, then you start pushing power out in the transmission system and the impacts associated with doing that. And how does that all get modeled? How does all the information get exchanged? When today, typically in most utilities, those are two very different groups, two very different functions, and they usually don't talk to one another. And then lastly, you'll hear this from anybody from SDG&E, rate design. Lots of discussion about, energy metering, lots of discussion about demand charges, demand charge avoidance, and the need to have rates that reflect cost to serve, needs that reflect the ability for SDG or any other utility to actually continue to operate and pay for its actual operational and capital expenditures. So one of the things here that I'll talk about now is really this whole idea of, how do you decide and how do you determine what the impact of DER is going to be? And this is a really pretty good summary. If you take a look at that seesaw, you can imagine that, prior to that big guy jumping on the seesaw, the guy on the right here is actually sitting on the ground, experiencing relatively low voltage. Once the big generator jumps on, raises the voltage. You can see here the nominal plus minus 5% ANSI range A. And if you operate under a CVR environment, you're typically operating from 0 to minus 5 volts. But fundamentally, these are some of the major issues that determine what impact, if any, DER will have. And you're really looking at where it's located, what type of circuit is it, and that tends to tie back into some of the other factors with regards to size and loads, et cetera. The type of circuit, whether it's urban versus rural, and what that tends to drive into is really sort of distance from the substation. Rural circuits urban circuits are, fairly short in length, fairly stout on the main feeder. whereas the rural circuits can go many, many miles, 30, 40 miles, in some instances, or even further. And then what's the circuit minimum loading? The impact is worse under low load conditions versus high load conditions. What is the circuit X over R ratio? So this is really the ratio of real to react, resistance to reactance. And at high X over R ratios, primarily highly inductive kind of circuit, you can solve some of these problems with simply reactive power. But when that ratio becomes low, then you really need a combination of real and reactive power. And then again, it's really the aggregate at the end, not the single unit, although if it's a large single unit, it can have a significant impact. And then really the voltage regulation. How is the utility regulating the voltage? As I said, way back when, 2 years ago, all we were concerned about was high load, max load, and low load, and making sure that the voltage was within appropriate ranges under those conditions. Well, and to do that, we would put out, in our particular case, we had load tap changers in the substation, as well as the line capacitors and line regulators when we needed them. And all of those have controls, and those controls originally were for unidirectional power flow from the substation to the loads. And increasingly, we're having to go back and modernize and retrofit a lot of those controls. Some additional maintenance associated with doing this. So let me switch gears here a little bit now. What's the solutions? Okay. So what historically, those solutions have been circuit modifications. And looking at and monitoring, ensuring resource adequacy for the actual system and making sure the voltage regulation schemes worked. You can look at demand response, and certainly at the sort of the system level, the larger level, where you're trying to work on the ramps, which I'm calling the slower rate of change of power events. That tends to work well, but for very high speed sort of solar oscillations, probably not going to be used in demand response. You get into 4-quadrant control devices, and we'll call these smart inverters, but whether it be utility dynamic power devices, custom utility storage, and or customers inverters and storage. And one of the people ask, well, why do you want smart inverters, and how many do you really need? And what we tell everyone is that ultimately we want them all to have that functionality. And one of the reasons we want them to have functionality, just want to make sure that we can actually sit there and accommodate the transmission system needs because it has the ag rate. And then lastly, one of the challenges in all of this is the rules and regulatory changes. So really energy storage for SDG&E, we've got immediate needs, near term, customers have needs, and then ultimately use cases drive technology choices. And that really challenges and barriers exist with regards to technology and the implementation of those technology. So what do we see as the storage value opportunities? We see, good operations, highlighted system operations, smoothing electrical transition, power quality, power leveling, peak load shifting or shaving. Storage for off-peak, on-peak AER arbitrage. When we get to negative pricing, arbitrage becomes a much more attractive enterprise. Then really regulation and ancillary services related to California ISO operations, and then the potential for T&D capacity deferral. So I'm going to try to speed up and shift gears, and we think about this now, and think about this in the context of, Ben talked a little bit about microgrids. There's really the utility, there's the military bases, campus environment, greenfield developments, and homes. From my perspective, I sort of view microgrids as an alternative service delivery model where, and it does make sense in various locations where it is the cheaper alternative than wires. So we have embarked on a project in Borrego Springs. I think a lot of you have probably heard about it. Really the goals were to enhance emergency readiness, increase the operational flexibility, and decrease the outage response times, increase the grid resiliency for this particular community, demonstrate new microgrid technologies, and ultimately increasing load capacity. This area is a single community, 2,800 customers, 15 megawatts, fed by a single radial transmission line, and it tends to go out quite frequently, and costs associated with the second transmission line is pretty significant. And so we're looking at the alternative service delivery model view of this. So, I mean, the values, microgrids looking to provide grid resiliency, higher level penetration of renewable energy, avoid adverse impacts, and ultimately taking the product and you heard Chip talk about DERMS and exploiting that system-wide to control distributed energy resources. And then you can see, on the particular graph on the lower right-hand side, this is the DERMS, distributed hierarchical control structure. Two figures on the left sort of show what happens in Borrego under sort of the monsoon, flash flood type of things in the environment in a desert, if you've ever been there. So we're getting close to running out of time, so I'm going to, here's the upper right picture is Borrego Springs. That's the actual microgrid yard. The white boxes are the energy storages there. We've got 1.5 megawatts for 3 hours. And then the upper right-hand corner of that thing are the two 1.8 megawatt diesel generators. We've been able to utilize the microgrid to keep all customers energized during transmission outage. And we've also leveraged the large 26 megawatt energy solar facility that you see in the lower right-hand side picture. And ultimately, we're looking to, how can we create a replicable model that can be utilized not just for SDG&E, but utility industry-wide. And so, I mean, with regards to the Borrego Springs microgrid projects or microgrid projects in general, we really have shown the first large-scale utility microgrid where we've actually islanded real customers as opposed to lab experiments. We've really looked at alternative service delivery model. What does that really mean? What's the technologies for future applications? And then I think one of the things that people talk about, low inertia environments. As we move forward with Borrego and operating just simply with solar and storage, we are seeing challenges associated with the low inertia environment. What does that mean? How do we have to actually control this? Again, established model to be used by the utilities, and then lastly, operate in a 100% renewable environment. And so with that, I will stop and happy to answer any questions.
Excellent. Thanks, Tom, and once again, thanks, Chip, for joining today. We got about 10 minutes left in the presentation, or 10 minutes left in our time together today, and a lot more questions that'll fit into 10 minutes. So we'll try to get through as many as we can. I'm going to start us off, just kind of ease us in. Tom, I know this is something that we've talked about in the past that's come up. We had a question around incentivizing west-facing solar, and if that's something that you're expecting to be a potential help for 6 p.m. ramp up that you're seeing in your territory, and kind of how that is looking as you get towards time of use as a mandatory rate structure in the future.
Well, so I would just couch it in the terms of the overall rate design. Where we ultimately need to get is rates that are representative of grid conditions. So if we have we're seeing our system peak move from 3 o'clock to 6 o'clock in the evening time frame. Clearly, if you've got your PV array oriented due south, you're peaking at 12:30, 1 o'clock. By 4 o'clock, there's pretty much very little capacity available left in your PV system. If you're into due south, you extend that, and you actually do help with the reduction in the overall ramp. And so what would that say? It would say that if you're looking at it from a rate design perspective, that there would be more value, i.e. potentially more cost avoidance or more incentives, or that's probably not the right word, but more desire on the part of a person to orient their array western facing, given the needs of the grid at that particular time versus in the middle of the day.
Excellent. So, Chip, to completely ramp this up to a little bit more of a complicated question, I think it's more of a definitional thing than anything else, but you talked a little bit about distribution energy markets as an important factor for distributed energy resource management systems. We had somebody who was kind of asking, is transactive energy markets, is that something that could be more impactful on DERMS and its penetration really than just a what is termed distribution energy markets. I think it's more of a relationship between those terms.
Sure. And yeah, the distribution market was intended to encompass both transactive energy as well as traditional rate design, and it'll be interesting to see regionally kind of which directions different markets go. I think the economics are going to drive the increase for most people are going to drive the increase in DER, and I don't think enough thought has been put into the transactive energy markets in terms of how this is going to be communicated, how it's going to be settled, where is that going to lie within the utility or within the ISO. So I think that is an area that we're following closely, and having worked in energy market software for 20 years, it's one I'm very much interested in.
All right, and we have one more question kind of on the market side of things and the rate design side of things, and it's kind of combining those two. Just looking forward for the distribution system, is it expected that rate design will be a more important factor for how distributed energy resources are utilized and deployed, or is a focus on getting a distribution energy market or a transactive energy market at the distribution level really going to be the kind of the primary catalyst moving forward? Might be a little bit of a trick question, but
let me take this, because I think it's an interesting discussion. I've talked at various places about transactive energy, and one of the more interesting questions is that when you contemplate that is, what value does that bring, and at what cost, and how could that best be accomplished in a manner that really benefits customers as opposed to just adding additional cost to customers. An example would be if you go to a purely transactive market where you got highly locational distribution pricing. Somebody pulls up in a Tesla Model S and buys one, shows up and starts plugging into your transformer that you're connected to 8 other customers with, for example. All of a sudden, I've got an overloaded transformer potentially, and therefore now my local rates for those other 7 customers go up significantly as a result of that particular customer making that economic decision to buy a Tesla Model S. Is that what people want? Is that what the regulators want? Is that what legislators want? You can extend that to say one circuit is on one side of the street and another circuit on another side of the street. Now you get into the question of, and they're 2 different circuits, therefore they have 2 different prices. So somebody on the north side of the street is paying $200 a month for their electric bill, and the person on the south side of the street is paying $100 per month for electric bill. Is that equitable? Is that fair? Historically, it's been socialized as a postage stamp, and as you think about moving towards that sort of transactive energy or locational distribution marginal pricing scheme, those are the kinds of questions that people are going to have to struggle with, and regulators and legislators are going to have to address, because typically we haven't worked that way, haven't done that way, and the question then becomes, well, what is the real value that gets unlocked because of that? And does that offset all the costs?
Yeah, I think that makes sense. So we have 4 more minutes. So I'm going to try and get through an additional 2 or 3 questions. I'm going to switch over to a little bit on the technology side of things. I think this is one we wrestle with in our microgrid coverage consistently, and often report on kind of both sides of the coin because of the technological similarities. But and I'm going to point this towards you, Tom. Could you comment a little bit on the relationship between distributed energy resource management systems and microgrid controllers, and a little bit on how are DERM systems as good as microgrids in terms of controls? Can microgrid let's just start with that. There's a secondary part to that, but it's a little bit more complicated.
Yeah. So the route that we've gone down is that the DERMS product, the Distributed Energy Resource Management Services product, is a, like I said, very hierarchical control solution. It's a peer to the DMS, ADMS. It's doing the optimizations, doing things, talking to these resources, and has able ability to do optimization and on a local level, and that the actual microgrid control component, that we see that as really sort of an application within the context of DERMS that can be enabled or not enabled. It's not necessarily a standalone. And some people are looking to do that directly via the a DMS, and other people are looking at it as a separate function and a separate system. But ultimately, from our perspective, whether it's separate or integrated, it ultimately has to be integrated, fairly seamlessly, because our operators, last thing they really truly want to see is another screen and another system. So.
Excellent. I think we have time for a couple more, maybe. So, Chip, I'm kind of curious. I know you mentioned a little bit on the kind of early stage of as you're integrating a particular DER into a distribution utility. Obviously, there's approval processes and there's data collection that the utility goes through. Can you talk us through a little bit of where utilities are as a whole, and when it comes down to doing enough to track DER in their territory to reduce integration pain in the future as penetrations increase?
Yes, in my experience, I see that process that there's a lot of silos in utilities in terms of the planning versus operation, and we'll also see various levels of tracking. Some people have DER in their GIS, many don't. So we see it all over the map, and so I think it does need to be better integrated. It does need to be better tracked. It may not be a problem now, but when you get to a point where it is, to have to go back through history and try to track all of that down, I think it'll be more challenging.
And just as a follow-up on that same question, Tom, we had one towards you. Obviously, your teams have gone through some of the difficulties of really ramping up the amount of information required and how that gets into operations, what needs to be getting into operations in the future. Can you talk through some of the lessons that you've learned on setting up, because I believe you guys even had some awards given to you for your initial stage sign-up processes and interconnection management processes. So can you talk through a little bit of some of the best practices you run into along that process? We may have just lost Tom. So I'm guessing we have a little bit of
I'm sorry. Yeah, no, I'm sorry. I thought you were talking to Chip. That's why.
Oh, yeah, no problem.
So what was the question again? I'm sorry.
Yeah, no problem. Just San Diego Gas and Electric has gone through a lot of effort to be essentially one of the leaders on collecting information on the early stages on the planning side of things with their customers as they integrate DERs. Can you talk a little bit about some of the lessons that you've learned that would be good for utilities to know as they're looking at potentially ramp-ups in distributed solar or energy storage or other types of distributed resources in their territory for kind of bridging that initial stage to planning to operation gaps?
Yeah, sure. So what I'd say is the key ultimately is to be proactive in this sort of whole discussion, because let's take sort of California. You see, there's parties, third parties out there that are selling products. We're seeing 2,500 types, 3,000 interconnections a month occurring. And if you look at that and take a look at the marketing and the development that has occurred in California and elsewhere, you're going to see that being basically taken into other states where there's really hasn't been that level of implementation. And then all of a sudden, if you haven't really started to consider this, or think about what tools do you have and what capabilities do those tools have, you're going to be, they're going to start to show up, and you're going to be scratching your head and saying, wait a minute. And then from our perspective, what you'll end up doing is you'll get caught by both the customers and the regulators for not being responsive. And so that sort of then rolls over into, okay, well, what do the operations folks need to understand? They pretty quickly need to realize that when they're doing switching operations, you're now looking at, well, what does that really look like? If I want to pick up a load off of a particular circuit that was de-energized, and I've got 3 or 4 megawatts worth of solar on that particular circuit, that's going to show back when I actually now close into that particular circuit. And if I'm not aware of it, then I'm going to create additional problems associated with trying to pick up and restore service. So it just creates additional operational complexities and planning complexities. And I think as long as you recognize that they're there and that you're going to need to address them, and the sooner you start thinking about how you're going to do that, the better off you're going to be. Hello?
Oh, sorry about that. It's definitely an interesting situation when they have that many factors being added to the equation when it comes down to management of the distribution grid, and it's something that is something definitely worth considering. So with that, we're actually a few minutes over on the hour, so we're going to close it. Finish up right now. We do have a lot of great questions in the till, and I apologize for not being able to get to those during the webinar. But I just wanted to quickly thank you again, Tom and Chip, for joining us today, and thank all of you out there for joining us as well. And have a good rest of the week.